All right, so welcome back everyone for our third lecture of the day on math physics, and back again in the direction of the mathematics of disorder. And this last talk is by Hongzhi Yao of Harvard, and his title is here, Delocalization of Random Band Matrices in High Dimensions. So welcome, and we look forward to your talk. Oh, wait a minute. Wait, before you talk, let's let Marcel in. He's a key member of the audience. I'm jumping the gun very slightly. We've been gradually merging towards 5 minutes past the start hour. Mm-hmm. So I think maybe we should wait for 1 or 2 more minutes here. Yep. I see 2 more. They're clearly, the trouble is you train them and then you start a little later, and then each time they're a little bit later each time. So we're now almost up to 50 people here. So I'll wait. I'm going to wait for until my watch turns to 50, which is in less than a minute.
You said about 5 minutes was the rule in MIT, and now
it is the rule in MIT. It seems to be the rule on the internet now. We're spreading our rules everywhere.
In Michigan, it was 10.
Well, Minnesota, had 45-minute classes because the campus is so huge. In the old days, anyway, there was 15 minutes for walking in between classes. In most places, it's about a 10-minute interval. Anyway. All right, I think we're ready to go. So welcome to the last talk. As I said just a couple of minutes ago, it's Professor H.T. Yao from Harvard University, and his title is Delocalization of Random Band Matrices in High Dimensions.
Right, thanks a lot for the invitations. And this is my first talk with Zoom, and also, it was a joint work with Fen Yang and Jun Yun. And let me try. And Yang is in the UPenn, and Yin is in UCLA. So I will start with some historical introduction. And so the Gaussian orthogonal ensemble is a random matrix of n by n random matrix, and it's a symmetric, and it's a normal distribution with mean 0 and variance 1 over n. And now, if you change the Gaussian assumption to be just independent without Gaussian, it's called Wigner ensemble. And typically, one label the eigenvalues. Lambda 1 to lambda n, they are n eigenvalues. The eigenvalues between -2 and 2. And the eigenvector, normalized eigenvector, is u1 to un. And the semicircle law is this Wigner semicircle, say the density is given by a semicircle. Then it was, when we talk about delocalization, one interesting thing is actually, even for the Wigner matrix, the delocalization estimate in this sense with high probability, this was only first proof in slightly more than 10 years ago by Benjamin and Schlein and early Schlein and myself. So it was quite strange. So how comes this was, people didn't consider this earlier? It was quite, anyway. So now the Wigner ensemble, there are many things one can extend the Wigner ensembles, and you can make the random matrix has correlations, and you can also consider some sparse models, and there are many generalizations. So I will not be able to talk any of these, and this is not a focus today. So what we are trying to see today is if you go beyond the mean field models, then what happened? Now, all this sparsity and all this correlative model and so on is still mean field in the sense that your metric are still, the metric element are still, still everywhere. Every single node can connect to very far away one with some probabilities. But the mean field one is quite different. So, but the mean field one is this random Schrodinger equation. If you look at the matrix, it's almost only on the diagonal, and there are a few off diagonal terms. So the other thing about the random matrix is the local statistics about the eigenvalues near certain energy. And the Wegener's vision is the statistics of the highly correlated quantum system is given by random matrices. So this was it's very, very and extremely bold vision. And now, but on the other hand, it's one can ask: is there a reason that we believe that the random matrix can model highly correlated system? So here I just cited a quote I often use is by George Uhlenbeck. He didn't believe the random matrix at all because he felt that the semicircle law is already wrong because probability distribution of the eigenvalue is not semicircle for most systems, and so he didn't believe any of this is correct because he say, well, if the density is already wrong, how can you believe that the label the correlation function is correct? So we can also ask a question like if the Wegener ensemble by itself is a mean field models, then why all this? Why do we believe that these non-mean field models like random Schrodinger equation and so on can be modeled by this kind of Wegener ensembles? This is quite. I mean, it's quite mysterious in some way. I mean, the typical explanation is this local interaction, they are joined together becomes has a global effect, but we never truly understand what's going on. So now, because there are many people already talk about random Schrodinger, so I will not say anything. Here, this was just the standard results is for the standard result is this. There's localization, delocalization, but there are result on localization, but on the other hand, there's essentially no result on delocalization case. It's curious fact that delocalization and the universality of eigenvalue statistics usually occurs simultaneously. So now this talk we want to talk about just one simple models, which is called the band matrix. Now, this is something we have been working on for about 10 years or slightly longer. You take a matrix and you fix a band. Whenever the matrix element with distance bigger than W, then you set it 0, and otherwise they are like a Gaussian distribution. And now because you set lots of these equal 0, so then your variance has to adjust it to get it correctly. Now, so this is 4x4, then the 4x4 still look like a Wegener matrices. But on the other hand, if you start to look at the case, this W, the width of the band matrix compared with the length scale of the matrix, then you can see that what's truly happening, this W actually is very, very small compared with the size of the matrix. Now we want to say we want to put this in a D dimension. So in a D dimension, you take a periodic boundary condition, and then you look at so your indices now instead of I and j, now you want to think about this is x and y, and each one is the lattice point. So then you still can you still can have there's a variance, and you still consider mean zero case. Now, so in this talk, I will focus on a case that this covariance, the variance structure is of the function f of x minus y divided by w times 1 over w to the d. And then we will assume that this f is a Schwartz functions, and then you sum over x, then this will normalize to be 1. And this was the correct normalization. So roughly speaking, your effective range is w, then you start to exponential decay or decay very fast. And so it's effectively, the effective range is size w, and w will be quite small. And now, so now usually in the random matrix, there's notation n is the number of the size of the matrix. Now this n is L to the d. All right, so this is the band matrix, and it was I mean, in some way, this is one thing it's much easier than Schrodinger random Schrodinger equation. On the other hand, it's also believed that to catch quite a lot of the random Schrodinger behavior. So I don't know if everybody agree, but there are many people consider this is the closest to random Schrodinger equation, but on the other hand, it's not a mean field model that one can think of, so that it will simulate the behavior of random Schrodinger. Now, so this is the model, and then the key object we will consider is the Green functions. So Green function is defined to be 1 over h minus z. And then this is eigenvector, and this is the eigenvalues expression, and this is Green function. And then the complex parameter is always energy E plus I eta. E is energy, and eta is the imaginary part.
So this is just the diagonal.
Oh yeah, you can also, yeah, we want to consider x and y. And then this is, you can define it off diagonal.
Right, but right now you're just.
Oh, I just write down the diagonal one.
Right.
Okay, so
maybe
I should write A and B, and then this will be UJA and then UJB.
Yeah.
And now if you take the trace, okay, you see I write the trace, so apparently I was thinking about a off diagonal term. The trace, then this is the so-called, this is called the stereo transform of empirical density of the eigenvalues, and it's called M of n. And then there's the MSC, which is the semicircle law, the stereo transform semicircle. And so, sorry, I'm not very good with this. I only start to use it, so bear with me. So we prove that the GIJ minus delta minus MSC, and is bounded by 1 over square root W eta. Oh, I think this is probably wrong. There's some W to the epsilon, but anyway. So this is we prove this bound with high probability if eta is W minus 1. Now the size of eta. Now the size, why all the attention is in the size of eta. The reason is the following. Now the size of eta, the size of eta is really like the inverse of a time in the evolution operator. So that's what you want to keep in mind. And now if eta, what we really want, usually you get a very strong result if you can get eta goes to 1 over n. I mean, of course, there's always some small errors. So if eta can go down to this, then you can see that because your typical eigenvalue spacing, your eigenvalue spacing, the distance is 1 over n. So once eta can go to comparable to 1 over n, you are basically, this Green function basically tells you the behavior of one single eigenvector. So that's why to get eta small is very important. And now, so eta, roughly speaking, is the eta you want to think about. Eta is the inverse of the time. Okay, so so now there's a conjecture. Well, I don't know how much is there's a conjecture. It's not really well. I don't know if people really stay in this way, but if one look at the off diagonal, if one look at the off diagonal term of the, if one look at the off diagonal term, then one expect that the off diagonal term is closer to the theta xy. And theta xy is 1 minus MSC of z f0 squared times s times MSC square of s. This s is the matrix of the, remember we have this sxy, which is the expectation of hxy squared. And this is the metric s. So roughly speaking, one expect that the off diagonal term is going to behave like this.
What was H? I've forgotten. Is it?
What is H?
Oh, is this
Oh,
the pair
H
correlation?
is,
H was something, wasn't called H before, was it?
The metric.
Oh,
like
it's
that.
the matrix.
Yes.
Oh, okay. All right.
Sorry. Yeah, maybe I'm going too fast. And
Well, that was just the, yeah, I didn't see
Yes.
that letter H before.
so the little h is the metric element, and then their variance structure is S. So you can see that if your S is, I mean, you can think about suppose you get this width W, and if S is all equal to 1, then this S is almost like a Laplace operator. I mean, it's not exactly Laplace operator. It's the Laplace operator without diagonal term. Without diagonal term. You take out the diagonal. So that's the S.
Mm-hmm.
So when look at this guy, then so one hope that this is the correct behavior. Now, if you compute this expression, this you can compute by Fourier transform. Now you can see that in the Fourier transform, this P is a dual variable, so it's really like a 1 over P square, and so this is, so it look like the green function of a Laplace operator. Now, so if you look at the behavior of this guy, and now their behavior is different depending on dimension. So you can see that in higher dimension, d bigger than or equal to 3. I mean, I'm here. I also write down the dimension 1, and you can also write a 2. There's a log. So, but never mind. So the important one we are focusing on is the dimension d higher. So d bigger than 3, it looked like 1 over x to the d minus 2. So in higher dimension, the green these theta functions, it look like it look at 1 over x to the d minus 2 is Laplace operator, but there's a certain range. The range is given by w divided by square root eta. So I will draw the picture in a minute. And then this is for eta before this w bigger than w over L squared. Once eta go below this, then we start to have a constant term appear. This is 1 over an eta term. Now, so the picture is like this. Okay, so I'm doing the mixture of the slide and this kind of talk. That's because I'm too lazy to transport all these slides into this note. Anyway, so this is the behavior of theta functions. It decay like 1 over x minus y d minus 2. So I suggest that you don't look at this. Don't look at the w squared. The w squared, one put it in at the end to make the scaling correct. So if you look at this one, it's actually look like a 1 over Laplace operator. And there's a range. There's a range how far you can go, and the range is w divided by square root eta. This is how far you will go. And then otherwise, once you go beyond this, start to exponential decay. So one would like to establish the off-diagonal term green functions. One would like to establish that these go like these functions, and the reason that this is you will behave like this is because this absolute value of m is 1 minus constant times eta. So this one is very, very close to 1. So that's why this guy behave like.
I'm sorry, I have just a notational question. So S is the inverse of Laplacian or Laplacian?
The S is a Laplacian.
But you seem to be operating with its kernel,
No,
with the inverse.
Just a second. So
It looks like S is the inverse, because otherwise you.
no, S is just this. S is so okay. So let me write it down just a second. So if you think about a Laplace operator, so then it's depending on your sign is 1 minus 2 1, right? And 1
Right.
and so 1 minus 2 and 1. So now we don't have a diagonal. We don't have a diagonal term. So the diagonal term will disappear,
Mm-hmm.
and the rest, what's left, is S. And
I
now,
see, but where do you pick up exponential dependence on anything? Because it's.
so this one, you can think so if you write down this one as if you write this as I needed some space. If you write this as m squared, 1 minus m squared plus m squared of s, m so s minus 1, I guess, diagonal term. Then this becomes Laplace operator. This is almost like Laplace operator. Okay. So the denominator is almost like Laplace operator, and plus this, the size of this is eta. So that's why the behavior of this object. If you want, if you want to think about a Laplace operator, then it's behave like eta plus or minus, depending on your sign convention on Laplace operator, minus Laplace operator. So that's the idea. So this guy started to behave like that. Okay. Now if you what's interesting, if you look at green function, if you do not take absolute value, so if you take a square of this guy, then it go like 1 minus m squared. But if you take 1 minus m squared, because it's a complex number, so the s plus, so this guy called s prime, s minus this is a complex conjugate. This one start to become like exponential decay kernel. And so this effectively is finite range. But on the other hand, this absolute value of gxy squared is very important. This one look like 1 over eta minus Laplace operator. So this is what one is looking. One would like to establish something like this is correct. It's like establish this picture is correct. Okay, so that's the that's a key question. And now now the delocalization, delocalization, it depends on what do you mean by delocalization, because we're not talking about a matrix. Oh, sorry, we're not talking about a matrix. We're talking about lattice size quite big, this size L, and then the W is very small. So in the strongest sense, the delocalization want to say that the eigenfunction will be sort of everywhere. It's called delocalization. But then it's not just that. So you want to say that if I draw a ball of size of L, and this L is equal to L to 1 minus constant, then you cannot have all the mass inside this ball. Inside any of this ball, you cannot have most of the mass inside this ball. Then this is called delocalization. And this is, but in the case of lattice, there's no such a concept or comparison of the scale. But now we are talking about the band matrix. So because we are talking about L is finite, so then there's you can talk about this concept of what's the scale of delocalizations. So now, the idea is the delocalization happens if the smallest scale we can go in eta, let's go to 1 over n, is bigger than the time to equilibrium. So this means so that, and now so this is bigger than this one, and then if you look at the inverse of this, is 1 over n is less than w squared over L squared. So this means this means that the condition L to the 2 minus D has to be less than W squared. And now is clearly, you can clearly see that in dimension 2, this is dimension 2 is strange anyway. So in dimension 1, this gives you L less than W squared, and this is exactly the transition width, the prediction. In dimension 3, in principle, this will give you delocalization in dimension 3 or higher. But this picture, this will tell this heuristic require that you can follow the green function up to a scale close to 1 over n, and this is very, very difficult because if you remember the talk of Erdős, so the time t was lambda minus 2 minus kappa, and so you can see so now here this t, whatever we want to do here has to go to you want to go to size n, which is quite large relative to lambda minus 2 minus kappa. So now this lambda, roughly speaking, lambda, you want to think about lambda is, depends on what you want. Lambda is 1 over W or maybe 1 over W to the D, depends on, because there's no exact definition. So roughly speaking, the lambda is something like this. All right, so now here, here's the main result. So so in dimension D is we assume dimension D is bigger than 10, and we assume that W is bigger than L to the delta for some delta positive, and energy E is away from the edge, and then then we prove that the green function is square is less than this theta xy times n to the epsilon. So this theta xy less than epsilon, and this holds for all eta bigger than W2 plus epsilon divided by L squared, and with probability 1 minus n to the C for C positive. So roughly speaking, we can, the time we can go is, if you want to think about in terms of time, the time we can go is, roughly speaking, we can go to L squared over W2 plus epsilon. This is near the time of equilibrium. Near the time that the random walk reach equilibrium. Now it's not that if you can reach equilibrium that you solve the problem. This is, the mathematics is quite strange compared with physics. Actually, if we want to go, eta even smaller, there are other difficulties start to see, and I don't know how to explain this, because in principle, if you think about in terms of probability, once you reach equilibrium, then you will stay in equilibrium forever. But the trouble here is this green function, or no matter you look at green function or look at this evolution operator, there's some memory effect. So even though you reach equilibrium, you have to be able to estimate the effect of the memory, so that something will not go wrong later on. So once you let time go longer and longer, even though you already reach equilibrium, you still worry about there are some memory effect will give you troubles later on. So that's why, I mean, this is physical explanation why so far we cannot go even further, but technically you were sure anyway. So this is the main result. And now oh yeah, I forgot to say, did I say Gaussian? Oh, sorry, I should put the so here is some. Now so it's good to have a slide so that I will not forget. So now the proof is written for the Gaussian case, and but one expect the similar method will work for other distributions. I mean, in random matrix, there's a big difference between the Gaussian and non-Gaussian. That's because in Gaussian case, there are lots of exact formula one can use. But that's only correct in the Wigner case. In the band matrix, the Gaussian case already contain the major difficulty because, and also that's because there's no exact formula for a Gaussian band matrix, or unless you use in supersymmetry, but that's a different story. So in any case, I will show you that later on that in our, what we have in our proof, we only use the Gaussian integration by parts. So the Gaussian integration by parts one can always replace by a Taylor expansion or cumulative expansion. So the method in principle will work for other distribution, but because it's already so complicated, so then if you use the Taylor expansion or cumulative expansion, then there will be a lot more term in Feynman diagrams. So then so that's why we only write this for the Gaussian case. And the second one is I already say a few times this is roughly equivalent to the evolution of Schrodinger equation, induce a random walk up to time t like this. But this still requires some refinement of our result, because if you really want to see the evolution operator, then the green function has to be much more precise. You have to compute the leading term, and we get a bound, and one has to compute the leading term more carefully. But I don't think this will be a main difficulty. So roughly speaking, what we show is if you look at this evolution operator, then one get a diffusion at least. So now the third comment I want to say is if you do this expansion of this operator, and by some method or think about this random walk picture, if you remember the earlier talk that at the end there was this kind of picture, there was this kind of wave, and then you do the scattering, this, and then there are lots of these wave, and you do a scattering, right? So now if you want to go to the time t of the size of L squared over W squared, now the number of collisions. So number of collisions will be, the number of collisions is L squared over W squared. This is a huge number. So if you have so many collisions, and then if you want to analyze the interference of this collision, and want to analyze this interference, this is very, this will be extremely difficult. And in terms of the technicality, this means you usually see the factorial in the graph counting. So if you see the factorial in graph counting, then you're going to see the L squared over W squared factorial. I think that the size actually is worse than this factorial, but anyway, if you see something like this, L squared over W squared factorial, and then you want to cancel these combinatorics by this oscillation, it's almost completely hopeless. So one cannot really do the naive expansion of this H expansion. This just cannot be done in this way. All right, so now roughly speaking, so this green function estimate can give us about the eigenfunction. It's the following two estimates. And the first one is if you look at the eigenvector, the eigenvector is less than W squared over L squared. I mean, this is quite small, but still, it's not 1 over L3D. The best result you like is 1 over L3D times some, maybe times some L3 constant like this. So this will be, and so you can see that there are still quite a lot of difference, but of this, if you really want to ask for the point-wise and you want to take the soup, oh, this alpha, of course, this alpha is, I cannot, this is to avoid the edge. Sorry, this alpha is away from edges. Okay. The standard, but on the other hand, one can get information of delocalization in the following sense. So this part is a bit technical. So roughly speaking, so I don't want to bother you with this this detailed mathematical statement. Roughly speaking, say the eigenvectors, which are exponentially localized in the ball of radius L, and this L is capital L to the 1 minus C for some constant C positive. The number of these eigenvectors divided by n goes to 0. So it means that the most eigenvector cannot be exponentially localized in any ball substantially smaller than the size of the system. So that's what it says in the eigenvector. This exponential localization can be improved a little bit, but it is too complicated. So maybe let's settle with this this kind of statement that says the eigenvector sort of spread out quite a lot. Now, so one may find this very strange. So how comes we after so many years of working, and it's something like such a trivial statement. The eigenvector is flat. For the whole system, it's so difficult to establish. Well, I don't know what to say because it's simply because we don't have any tool. The only object we know can tell us something about the eigenvector is the green functions. And then the green functions, if you look at green functions, so the green function, unless the green function this eta parameter are very, very small, close to the size of the typical spacing like 1 over n. So then this eta, practically, if you really want to do the strongest case, the eta practically is 0. But if eta practically is 0, this object is actually very, very singular, because once you get close to eigenvalues, you can see that the major effect is from that eigenfunction. So unless one can study this one with this eta very small, otherwise we don't really have any tool to deal with this eigenvector. If you write down eigenvector equation, then you also don't see very much, and so that's why. All right, so now so in the remaining maybe 10 minutes something, so I will explain some of these ideas, and I will explain why this where this theta comes from. And oh yeah, so here's some previous results. So I forgot. Maybe I should first say this. So now this is a partial list of previous works, and actually there are quite a lot more. I only did some of them. So in the D equal dimension equal to 1, and then this W has to be large. It's L to 3/4. One proved both delocalization and universalities, and this was joint work with Bourget and Yang and Yin. And then there are partial results, I mean, not as good as 3/4, and which also joined with Erdős and Antis. And then there are quite a few papers. It's some combination of authors. So now this one has no Gaussian assumptions. And in the delocalization directions, I think the main person is Schenker. Schenker did a paper, and then he wrote another one. So right now they know that delocalization occurs in W less than L to 1/7. So then in one dimension, using for the complex band matrices with this means Gaussian. So this actually is Gaussian. For complex Gaussian band matrices, and then they require the covariant structure. So this is so now maybe I should say something. the covariance matrix has to be equal to 1 over, I guess it's some constant minus Laplace operator. So they require that the covariance matrix has a spatial structure. And then, but quite remarkably, they can do the W close to square root of L. And when the W close to the square root of L, they are able to, W bigger than, I guess. So I didn't really remember this perfectly. So W is slightly bigger than square root of L. And they can compute a 2-point function in a complex case. And it's a remarkable, yeah, I mean, she can do it because this supersymmetric functional, this after reduction is still in very high dimension. I remember the dimension is, okay, I mean, the following is just by personal conversation. You should check the paper. I didn't read it. So the supersymmetric matrix still has 60 dimensions. And then due to some symmetry, it started to reduce to maybe 16 or something, but then they were able to analyze this precisely. So they will be able to get close to square root L. All right. There are also high dimensional results by Yang and Yin, and there are quite a bit of previous work by, especially by Erdős and North, and there are also some other work. Okay, so the next thing I want to do, I want to explain to you why this structure, where this data, this structure comes out. Yes, yeah. It's why do we get this object? So that's the main question. So so the idea is the following. So this part will appear in the previous work, but so let me explain the idea. And so look, you have green functions here, and green function is h minus z. So what can you do? You add a semicircle, and you add and subtract. Of course, you can try to do more sophisticated. You don't have to just use a semicircle, but semicircle at least is the leading term. It's correct. So you add 1, you subtract this. Now you do the resultant expansion. So resultant expansion, you expand this h plus m, and with respect to this m plus z. So you get the first term, and then you get a second term. All right. Now, so now so then one take this equation and rewrite slightly. So this minus 1 over z plus m, because z plus m times m equal to -1. This is some special property of semicircle. So then you get g minus m equal to m squared of g minus mhg. So the h here is quite will be important. Now, so now if you look at green function gxy, and then you look at gxy complex conjugate. So you take you want to think about. I want to take expectation with respect to hx. So roughly speaking, is maybe I should draw a picture here. So if you have a matrix here, and they say this is x, okay. So now you want to take expectation with respect to this whole column and this whole row. But for band matrix, of course, this expectation is only, they're only, okay. So for band matrix, they are only the element is only here and here, okay. But in any case, so one denote that the expectation with respect to this column, this row, by px, and the q of x is 1 minus this expectation. So this decomposition means decompose things into this expectation roughly correspond to its mean, and this q roughly correspond to its fluctuation. So now you take this one, so you separate into the fluctuation part and minus the expectation with respect to this column and this row. And now in this expectation part, this G, the GXY here, this G, I use this formula. So I plug in this formula here. You'll become like this. So I know that this part is it's hard to follow. So so don't look at equation too closely. And roughly speaking, then you just do a resolving expansion on the green function to the first order. So you do a resolving expansion of green function to the first order, and now then this h of x alpha, because you are taking expectation, so you can do the Gaussian integration by parts. So Gaussian integration by parts, your Gaussian integration by parts, you can act, the Gaussian integration by part can act on this one, or you can act on this one. So there are two terms. So Gaussian integration by part, you can act here or you can act here. Now, the main term is the Gaussian integration by part acting on this gxy bar term. And this term, because when you do the Gaussian integration by part, you will pick up its covariance here. So your covariance is S, and then the Gaussian integration by part will give you G alpha Y, G alpha bar Y, will give you this term. So this will be the main term. And then there are some other terms this will cancel out, and so I will not get into detail. And then you will see that when you do integration by parts, this give this term, but there is also a gxx here. But the gxx is the green function diagonal term, but the diagonal term of green function, we always replace the diagonal term of green function by m. So this one replaced by m bar, and then you get m squared here. And this is m squared times s times g. Okay. And then there are some other terms which you will cancel. And so at the end, if we define something called a t, we define something called t, and t is a green function, absolute value squared, take some average with respect to s. And now all this calculation here is x not equal to y. And then you also look at the main term of the diagonal term when x equal y equal to x is equal to m squared. Then roughly speaking, then the calculation in this page will give us the t will equal to m squared times s and times m squared s times t. So this structure here, this additional s will translate to an additional s here. So we get a t plus m squared s plus m squared st and plus fluctuations. And now this, so I move this to the other side and divide this over, and I get this equation here. So I get this leading term. And then this term is fluctuation and error term. And this was done with Erdős and Knowles and In. And then we put some estimate on this one, and we get some result about, this is how one gets result about the previous result was mostly done by the so-called T equation equations. And now, I still have 4 or 5 minutes. So now let's put this into a graph languages. So roughly speaking, what we put, the previous expansion is if you look at the t, the leading term, it's from x to 1. The leading term is this one. This one now is a double line. This double line is behave like a theta, and then one can follow the arrow term. The arrow term will look like x go to alpha. Oh, sorry, x go to alpha with a theta line. What's going on here? So this is theta line here, and now from alpha you will connect to a beta, and then here there's a g, and then there's a g bar. to y. And the other thing, the other one is from alpha connect to beta. So here is a beta here, and then beta connect to y. So, and this widow line, this is the S line. Remember, when we do integration by part, we always have the S line. And now we also have a weight. We have a weight. This is delta. Delta is because every time we replace a diagonal term, by diagonal term minus m, and then later on this diagonal term minus m will expand. Will have to expand. So this guy here has to be further expanded. Now the one major problem here is all the expansion is in terms of WD/2. So if we expand object like WD/2, so it's going to be a series expansion like this. And once all this is mixed up here, it's terribly complicated. So so the main so now if you are given a graph like this, we assign a degree. We assign a degree is so now let me not to bother you too much with how we assign a degree. That's because when you write down this object in terms of integrations, it's really a summation. Then you can count each of S is size 1 over W3D, and then there's also theta line and also this green function line. So if you count its order if you count its degree in terms of WD/2, then each graph you can assign a degree. And so expansion is in terms of degree of WD/2. So maybe let me not to bother you too much because I don't have time to show you the detail of this degree. Roughly speaking, our idea is this last line is we are able to extend this T equation into an expansion to an nth order term. So this expansion to an nth order term is the first order term is theta xy. This is the previous C, and then there's a self-energy term here. The self-energy term will look like theta times the self-energy times theta. And then there's a higher order term, and plus this term is fluctuation and error. So anyway, we don't have time anyway, so this fluctuation is out. And so don't look at this term, this fluctuation and the error term. The key is the self-energy term is of this form, theta times sigma times theta. And then there's a higher order term. And now there's an important property of the self-energy term is that the self-energy term in the limit is satisfied the property the summation over the indices y actually vanishes. So this is a key property. If we don't have this property, then this expansion will become a divergent expansion. But this property makes this expansion sort of become useful. But in any case, I think I don't have time. I shouldn't keep on going. And so so the summary, the key idea is the T equation, expansion, T equation we in the previous work here. Now this term is the theta, and there's the fluctuation plus error term. But now here we find that we can make this term much more precise, and it's much more precise in the sense that there's a term like theta times the self-energy term times theta, and this one has a mean zero properties, and then there's a higher order term, and this expansion we can do this expansion for all the n, essentially for all n, and that's why I mean there's a precise equation condition for n, but I don't want to get into. So this expansion essentially this n is arbitrary. It's quite actually this n at the end will depend on log L divided by log W. So this expansion makes all we can extend the previous method and to get this green function estimate. So thanks for listening. Thank you.
Okay, thank you. So before I break for questions, could you move one down and we'll look at the definition of TXY? the definition, which is just
Oh, Txy is
it's just in the statement of the definition.
yes. The T.
Yeah, here it is.
Yeah, here. Yes.
Yeah,
Yes.
right. So the S's this has this has the eta, the complex dependence in it.
No,
is
no,
that,
no, no. This
or is
S
this S is real?
no, this S. If you think about S is Sxy is 1 over W to the D. Oh.
Yeah. So this is a positive. This matrix
Yes,
has positive
yes.
entries.
Yes, if X less than Y, 0 less than this, less than W.
Yeah. So it's just got positive entries.
It's basically the average.
But now you're splitting it into these things which have zero average, right? I mean, in other words, it's right. There's some kind of very complicated alternating sum for this positive quantity.
So if you look at this, if you look at this at the end, you're talking about this final one here?
Yeah. So the point being that you have a positive matrix, but when you break it up into pieces, you're breaking it up into
yes.
This
one is still positive.
Yeah.
And this one is positive, but their difference break into lots of terms.
Lots of terms which are of very alternating things.
Right.
And somehow the fact that many of them are mean value, you can break them up into pieces that are mean value 0.
Yeah, that's right.
Is more or less the key.
That's right.
So
you can keep the mean zeros decomposition for all decompose into degree, and then each degree has mean zero property for n fairly large. Mm-hmm. And now the size of n one goes here is this. Well, I think it's more important if you want to think about comparison. This eta is W squared over L squared. So that's the effective how much n you can go is if you want to W to the minus n is roughly d over 2 is roughly this guy. So you can go very, very high order. And this order actually depending on this you can see, well, I mean from this formula. So if you want to think about the number of recollisions in the previous talk, René Schrodinger, so the number of recollision one can deal with here, it's truly a lot more. But on the other hand, this is Toy model. So
it's L squared over W squared collisions.
Yes. Well, the eta is this. So the number of collision is roughly speaking is this guy. This number of collision.
All right, so thank you again, and let me open it up for questions. We do have time for questions here.
So first of all, thank you for a wonderful talk. It was mesmerizing.
Well, thank you.
But I have a question. So you expect that the estimates are sharp at this point, meaning that if you actually want to get better theorems, ultimately you need a different expansion, or you need to be better at estimating this one?
Well, I think this. I think one has a chance that if you do a more refinement of estimates, you can get eta smaller. But how small the eta one can go, I'm not sure. Mm-hmm. So, but I think the idea of this decomposition is probably correct, and I mean correct in the sense that one may be able to use this to answer the question eventually. Mm-hmm. And this meaning that I don't think take eta go to. I mean there are various questions. If you want to get the eta, so right here. If you want to get the eta, go down to 1 over n times n to the epsilon. So I think that there's a chance one can do that. But on the other hand, don't forget we take a W equal to L to the delta, and delta positive. But the you can ask a harder question. So suppose W is large and L go to infinity. This is much harder. So you see, in this case, even if I can get eta equal to 1 over W to the W, it's still finite, still not infinity. So there's some subtle difference, and even if you get another W, it's still finite. So when I make this assumption, in a way, it's a cheat. I mean, well, cheated depends on what you mean. Once you get this, then you mainly just want to get W to the n for n large but finite. I mean, this is roughly what you say. But eventually you want to say that the eta can go to 0 for W fixed but large. But that's much harder. I think for Rand and Schrodinger, any of this setting is already, anything like this, it's already incredibly difficult.
But you're shooting into delocalization regime, right?
Yes.
So do you expect that this expansion could bring anything for better than 1/7 power as far as localization
Oh,
goes?
it was in I think if you, well, I don't know, what should I say? I think if one compute this guy in one dimension, if one can get good hold of this one, where you get T, or anyway, so.
That's exactly
if you
what
get T, get very good estimate on T, then you will see the exact localization length correctly. If one can do it, but lower dimension D equal to 1, lower dimension lots of countings and so on are different. But the idea of using the T, I think is all right, because if you I think in dimension 1, if you get green function estimate correctly, then you will see both localization and delocalization. That's not a problem.
So you think it's, I mean, yeah, so the question is, it's as David has pointed out, as you have pointed out, it's an oscillating expansion and there are cancellations. But
yes.
In principle, you expect that the terms are sort of in order already. So you should see in the leading term post localization and delocalization at the correct scale.
This guy give you the correct behavior in D equal to 1 as well. So.
Thank you.
Other questions? I still want to go back. Oh, here. There was something in the chat. Maybe I should monitor that. I think people are some people are checking out because it's late in Europe right now. But let's see. Can you go back again to the definition of T?
Yes.
So that there were in the localization. Do we just pass by it or?
Yes,
maybe.
That's right.
Ah, yes. Yeah, here it is.
Yes.
Right. So again, you're multiplying the matrix X with S, which is essentially for you, it's almost 1.
That's right.
This function. Well, I mean, it's a constant
yes.
on the band, right? Yes. And then you're just multiplying. So there is still this parameter Z, which is the complex. You're pushing out to a certain time scale. You want to get closer and closer to the honest Green's function right at the spectrum. But you're multiplying the square of the matrix. I'm trying to understand. So there are these other quantities. Maybe it's Molchanov who first. I can't remember who first used the fractional powers, and various people have used different quantities to get a hold of the eigenfunctions. And this one seems to have an interesting recurrence property, as you've shown.
It's You know, the Eisenman-Molchanov, they use fractional moment, and you know, fractional moment has some advantage in trying to deal with the singularities, but that's mostly mostly they used to deal with this singularity of energy minus z.
Right, right.
And because now here, but on the other hand, if you start to take fraction and so on, then you cannot use. It's difficult to use the expansion method because once you take expansion, you take fractional power, then you got lots of headache.
Right.
So if one goes to fractional moment method, then your goal is to derive inequality. You want to derive inequality and try to, from the inequality, to deduce your result. But what we are doing here is different. What we're doing here is we essentially want to compute the object quite close to what it is, and from here to get the result. Now for delocalization, I don't know any inequality, you know, any argument based on inequality so that you get some result.
Well, so maybe I'll put it slightly differently. You're using matrix multiplication.
Yes.
Right. And
now actually go ahead.
They have to abandon. I mean, because they're using these fractional and they're taking the expectations. They can't possibly use these kinds of algebraic tricks. But I'm just hoping that there's some other non-local quantity that still can still make use of matrix multiplication or some formulas. You know, it's magically.
Yeah, it's so you know what we are doing in the absence of a better idea. So.
Yeah. All right. Well,
all right.
I'm going to wait for one whole more minute, and then we'll relax and take a break.
Sorry for asking the second reference question for the day, but is there a reference for this? Because I mean, the 2020 results seem to be super new.
This one we have about we have a draft about 100 pages, but probably it still take a few months to completely finish it. Okay. So I will send it to you once we have a
it would be greatly appreciated, yeah, even in a drafty form.
Yeah, all right.
All right. So as I say, I'm going to hang on for what's our next session time? I'm not sure. We're just having Q&A at some point. Is it at 2?
Yes, I think the next one is going to be.
Well, I should check this. Unfortunately, I have my view option, so I can't see anything else here.
It says 2. I think it's 5 minutes.
2 o'clock. Okay. All right.
Okay.
So I'm going to standard time. That's in about 5 minutes. Somebody's going to show up. Anyway. Okay. Right. So thank you, everybody. Thank you. Yao and everybody for great talks this morning.
Thank you.
Afternoon. So long.